Okay, thank you. So I chose this topic probably because it was the last topic I was discussing with Andrei, mathematical topics. And it was some time ago because unfortunately I missed him when he was in Masarai. I mean, I met him only once, but we didn't talk mathematics. We talked some other stuff. And I would write, it's actually a project which I go to for several times. So it's actually 3 installments of these, 2 already published, and the last one is very new. So let me write down, this is with collaborator, Grantcharov. And the inspiration for this work comes from 2 sources, 2, in my opinion, very important works, and this is just for inspiration. One was an old paper, or a couple of papers by Gelfand and Ponomarev, where they studied the composable representations of the Lorentz group and came up with the quivers. And actually, it was very influential paper in quivers and in representation theory. And then another work of Zergel, where he somehow proved that the category O can be described in terms of certain quadratic algebra, and that leads to further works of Kasul, duality patterns, etc. So, so in this spirit, we would like to treat some other category of infinite dimensional modules over a semi-simple Lie algebra. So let me start with the definitions and a little bit history of the question. So they assume that G is a semi-simple or even reductive Lie algebra over C, and we fix the Cartan subalgebra in it. And so we consider modules semi-simple over H. So we think that our module M has a weight decomposition. So each of these is an eigenspace with respect to the Cartan subalgebra. By support, I call the set of non-zero weight here. And one condition which we would like to put more is that the dimensions of these weight spaces are finite. So the first person who, so maybe I give you right away a couple of more definitions. So this is called the weight module. So we say the weight module is bounded. If all these dimensions are uniformly bounded by some constant. And we say that the weight module is cuspidal. And so here it is pretty clear that if I pick up any root and the root element in G, then it maps mu to mu plus alpha. And so the module is called cuspidal if this is an isomorphism for each root vector. So the first person who started to study these modules systematically was Fernanda. And in particular around 90, I think 91 maybe. And in particular, he proved the following theorem, which slightly explains a little bit this terminology, that for any weight module, for any simple weight module M, for any simple weight module M, there exists a parabolic subalgebra G in G, and the cuspidal simple L module S. So now L is a Levy subalgebra of the parabolic such that M is a quotient, unique, simple quotient of the parabolically induced module. Induced module of S. So this is so-called parabolic induction theorem. So in principle, it tells us that if we want to classify all weight modules, we are basically interested in classifying cuspidal modules. And so many people were actually working with this, and there were partial classifications. I probably missed some names, but I think Bankert and Britton Lemire and a lot of other people were working in this theory. In particular, they classified multiplicity-free modules such that every such dimension is 1. And then actually complete classification was given by Mathieu. Classification of simple cuspidal modules was given by Mathieu around 2000, I think. So this is the classification. And so the idea actually, you see, it's actually related to the bounded modules because it is clear the cuspidal module is bounded. And what Mathieu was able to do, he was really studying, you see, modules in the category O are also such weight modules. So he classified bounded modules, simple modules in the category O, and then somehow he was able to move, and I explain it a little bit later. He used certain localizations to construct cuspidal, all simple cuspidal modules. I just want to mention one important thing, which already was noticed by Fernanda. So suppose M is a bounded simple weight module. And suppose it is infinite dimensional. It's not very difficult to see that the Gelfand-Kirillov dimension of such module is 2 times the rank of the algebra. I assume here then, of course, that G is semi-simple. So therefore,
how does the radical of the parabolic action S?
Oh, of course, I didn't say it. Lx, as it should, and the radical x by 0. Radical of parabolic x by 0. So it's in a little bit like you do with highest weight. And the highest weight, although you leave this is a Borel, P is a Borel, and the high.
Why is it 2 times
Oh, sorry, it's wrong. Sorry, you're right. Sorry. This is my mistake. What I was trying to say is these two comes in the next sentence. So if you know the Grantcharov dimension, you can look at the associative variety of the module, which is some nilpotent orbit. So in order to have such modules, you need small dimensional nilpotent orbits. So you should find nilpotent orbits of dimension 2 times rank G. And for simple G, such exist only for type A and C. Okay, and then you can really, there is a very easy way to produce a lot of such modules if you use a certain geometric realization of these modules via Weyl algebra. So the classification goes like this. So it's a little bit more interesting. So it's a little bit more easier to study the type C first. So I briefly formulate the result about type C. So we are talking about the Lie algebra SP2N. And we all know that it could be embedded in the Weyl algebra of n variables via Weyl representation. And the Cartan subalgebra here goes to the subalgebra here generated by Ti di. And this is actually maximal, the subalgebra, associative subalgebra generated by this is a maximal commutative subalgebra. So you can study weight modules over AN. So let's call this AND. And so it makes sense to study weight modules over D. So the problem which we were addressing after this classification was trying to understand the category of bounded weight modules. So let B and try to understand what kind of algebra or quiver wave relation is responsible for such category. And so the first result so of course, like the situations of category O, we have blocks, and we really describe just the blocks. And so here is the first result. That in case every block in B is equivalent to certain block in the category of weight modules, weight D modules. And actually, it's not very difficult. Such blocks are enumerated by numbers up to equivalence. corresponding category is equivalent to category of, so the block BK, I would say, maybe I should just say BK this way, is equivalent to the category of Z2 to the K graded modules over quadratic algebra say at theta 1, theta k, quotient by the relations that all theta I squared are 0. So this grading, I'm assuming that each of these has a grading 1, 0, 0, 0, and 0. They do commute, yes, they do commute. So in terms of quiver, let's say we take k equals 2, then we really, you see this condition that our modules Z2K graded gives me the idempotence. So for k equals 2, I have the quiver like this. And so if I call this alpha, this beta, again, beta, alpha, then I have alpha beta equals beta alpha, etc. going like this, plus I also have that alpha squared and beta squared are 0. Okay, this is not a very difficult theorem. As soon as you are able to prove that going from SP to AN, in principle, you see, if I look at the universal enveloping algebra, I have a pretty huge kernel, and I might have extensions which are not coming from this, and this is the most difficult part, because now when you reduce the whole thing to the Weyl algebra modules, the Weyl algebra, AN is a tensor product of A1, and so in a sense, you study it for A1 with just quiver like this, and then you work out the tensor product. Okay?
So BK is a tensor product of K copies of B1, which is a block.
Exactly, yes, yes. But you see this K, it really depends, yeah, for any AN, you have all possible Ks. And it is also more or less clear, because for B1, even here, if you look at the SL2 modules and try to draw their support, so in most cases, you have just one reducible module, and then it's a completely trivial case. When k equals 0, it's a semi-simple thing. But you have also the possibility that your module is divided in two pieces. And that gives the two reducible pieces, and each of them corresponds to the vertex on this quiver. Okay? And then you do the tensor product. And then we started to think about SLN. It is more interesting situation. So now I assume that G is SLN. B denote the category of bounded weight modules. And I would like to talk a little bit about blocks now. So here is the point. First of all, it's not very difficult to see that all these bounded weight modules, or any weight module really, is finite over Z of G, as in Bernstein talk. And therefore, this stands for central or infinitesimal character. But this infinitesimal character might be generalized. So it's And it's not very difficult to see that, of course, that gives you the splitting, right? Whenever you have two different infinitesimal generalized central characters, there is no extension. But there is another thing there. You look at a set of weights, the support of M and the support of N, and if you have a non-trivial extension between M and N in this category B, then support of M and minus support of N must be contained in Q, which is root lattice, which is clear. The set of weights must be different by the root lattice. And therefore, this stands out what kind of support my modules have. And this is a parameterization by H star, the set of all possible weights, quotient by the root lattice. So, and at first what we were able to do, we were able only to classify the blocks which are sort of only corresponding to the cuspidal representation. So let's see, be the category. So when we have blocks of two type, from the point of view of the category C, and so the first is type is just equivalent to the category of finite dimensional modules or nilpotent, category of finite dimensional nilpotent modules over the polynomial algebra of one variable. So assume that Z is locally nilpotent. And the second block is, and that was a very nice, actually, was equivalent to the category of the fallen quiver wave relation. So what I'm going to do, I have n minus 1 vertices exactly as in the Dynkin diagram. And I put x and y like this, one after another. So I don't know what I get here. Maybe x and maybe y, depending on the parity. Say it y. And x, and I have this condition that xy equals yx equals 0, and this is the relation. So this is a very famous particular case of the Gelfand-Ponomarion quiver. As soon as we get this, representation theory of this algebra is known. And it's very beautiful. You can it's still a tame algebra, but it has the set of undecomposable representations enumerated by one continuous parameter. And it's also a Kazula algebra, which is possible to prove here. So the point is that basically the condition that the block is cuspidal means that none of the mark of this weight is an integer, okay? And so the more there are more integer marks here on this parameter I have, the more difficult the situation becomes. So now I want to talk a little bit about functors, which are useful for studying this category. So one of them is very well known in representation theory. And so this one allows me to go from block with one central character to another central character, not vary in the support part. And this is so-called translation functors. So this is the tensor in the finite dimensional modules. And then projecting on the corresponding character. And this already, there is this, actually there was this theorem of Bernstein and Gelfand. He tells us about equivalence for certain such things. And it could be, of course, done in this category. So using this translation functor, we can prove that an EB chi is equivalent to the category to be okay. So this infinitesimal characters are enumerated by weights modular Weyl group action, and so really the point is I can't have an arbitrary character, infinitesimal character, very very specific one. So and up to translations, it's going to be, I can make it the corresponding with weight proportional to A pi 1, where pi 1 is the first fundamental weight. So A can be anything here. Okay. So you can have more blocks, but they all are obtained by equivalences. So from point of view of the algebra, which is responsible for them, they are all equivalent. So the next thing which I have to do, it's not a very difficult thing, but the point is if I study this category B, I immediately see that I don't have enough projectives in it. So the idea to use the standard machinery of Gabriel, I need to do something more. And what I really do more, I do the completion of the category B is a completion. And so what I do, I really and the direct limits, and then my category has enough injectives. And the last functor, which is very important in the situation here, I explained to you how you can vary using a functorially go from one infinitesimal character to another one. And then I'm going to explain to you that you actually can also vary the parameter mu without varying an infinitesimal character. And so this is so-called twisted localization functor. And this is the following. So you look at your universal enveloping algebra, U of G, and you pick up the set gamma of orthogonal set of mutually orthogonal roots. And then I have corresponding commuting elements. So what I can do, I can localize my universal enveloping algebra with respect to the corresponding multiplicative set. So I'm going to consider U gamma, which is localization with multiplicative set generated by X alpha. And I have to write down the formula here. Yeah. So for any x, which is actually, so let the number of this, so let k be the number of such roots, and let x be any vector in ck, when I can construct theta x gamma, which will be an automorphism of the corresponding localized algebra given by so you see the action of these root vectors here is locally nilpotent. So this is actually well-defined sum. And so what I can do with any module M line here, I can localize it and consider it as a module over U gamma. When I can twist by this twisted automorphism, I get another module over U gamma. And then I can look at it as a U module. And that gives me the functor, which gives me the shift of the support of my module if it was a weight module. So I call this functor dx gamma. And the shift is prescribed by the corresponding vector in ck. Okay, and so what, how I construct it, I start with a module M, then I localize. When I use this twist, and when I restrict to U modules. And that is a nice functor which does a lot of nice things. In particular, if I work in the complete category, is also well defined and it preserves injectivity property. So it's very useful since dx gamma is exact and maps injectives to injectives. And so now I would like to approach the problem of description of such blocks using again the Weyl algebra, or rather something else really, which is the algebra of twisted differential operators on the projective space. So again, let D be the Weyl algebra of n variables, and think about it as differential operators on the affine space An. And then clearly, since SLN in an obvious way acts on An, we do have a map from the Lie algebra to An, just the vector fields action. And therefore, we have the corresponding homomorphism of associative algebras from U of G to An. Okay, but of course this map is highly non-surjective, and the main reason for this is that I do have the Euler vector field xi di, and it's not very difficult to see that the image is really lying in dE, the centralizer of this Euler operator. So if I call this map phi, then image of phi is lying in dE. which is everything which commutes with E. And so I'm going to define the algebra D with a little a here, which is dE quotient E to the minus a. And what is this? This is a globally defined global twisted differential operators on Pn minus 1. So in order to study my category, I, however, should study another algebra, because the whole point of this map is that the center of the universal development algebra under this map maps to the polynomial algebra of E. Okay? And so the action of my center is only finite. It's not, it doesn't have, it just has only generalized central character. So what I really have to study is this limit. Okay, so now I think I'm more or less ready to explain the result. So I can talk about weight dA modules, right? And somehow this number a is actually responsible. So what I really saying here, that if I have a weight module over dA, I can lift it to a module over G. And so therefore I have a functor. I will write it like this, a weight dA modules. And it's a simple calculation to check that the image of this functor is going to be in exactly with this central character. This is A here. And so I do have such a functor, and the question is, is it really equivalence of categories or not? In general, it is not, unfortunately, because there are three cases. One which we call non-integral. So when A is not integer. And the second we call a singular integral. And this is when A is between -1 and 1 minus n. And those are exactly why these numbers, those are exactly, if I want my O of k do not have any cohomology at all, a cyclic sheaf, this gives me some special situation here. So let me just remind you that hi of Pn minus 1 OK is 0 for all I, exactly if A is from this set. And then, of course, there is this last case, which is a regular integral, where A is anything but these things here. The trouble with this regular integral, that I can't really realize the whole category here. What I have to consider instead, I can consider the Durham complex. And then somehow, what I'm claiming that any reducible module from the category appears as a certain subquotient on the de Rham complex on Pn minus 1. Okay? And so, in two first cases, 1 and 2, we do have that this functor, I don't know, I call it psi. We do have that this is an equivalence of categories. So that would be probably theorem 3. And in the last case, we still don't know complete answer. It's still an open question. I don't know if I have time to explain why it is an open question. I first would like to formulate it first. These two cases. Okay, so I do know now that I should study certain weight dA modules. But how to do it? Okay, because what I really want to construct certain quiver, for example, which is responsible for this category. And what I really do, I start with the weight modules. With finite dimensional, with finite action of E. And this category, again, is very easy to describe and almost in the same way for what I did before, but there is one, so maybe I should, again, we do have the algebra, which I call CK. It's going to be slightly different algebra, so we consider Z2K graded. And the algebra which we have is again the algebra of polynomials theta 1, theta k, but the relations which we do have here is theta I squared equals theta j squared for all I for j. This is again the Kosole algebra, by the way. So maybe I should quickly explain just why I do have this relation, because it's really, I'm going to show you one particular injective module. No, because it's, you see, you have a variable u, and this is responsible for the logarithmic extension of modules. So you will see in a moment the Clifford algebra, because it's a Clifford algebra in the polynomial algebra, I would say. Right, something like this. It's also, you see, it's commuting, not anti-commuting. Yeah, I can actually, I can make it in a sort of Clifford algebra. You're absolutely right. So, yes, but I really wanted to show you this example here. It's a little bit, can't find it here. Okay. So we have the Weyl algebra generated by Ti from 1 to n and Di I from 1 to n. And so what we're going to do, we're going to pick up, so the whole point is that from the point of view of Bernstein talk, of course, the Cartan subgroup of maximal torus is not spherical, right? Because it usually doesn't have an open orbit on the Flach variety. But of course, here it has an open orbit, and that's how it all plays. That's really the reason behind all this. So let us consider T to the lambda, so which means actually T1 lambda 1, Tn lambda n, and then consider the Laurent polynomials. And then add one more thing, namely the logarithm of T1, etc., Tn. And so we consider the polynomials of all these variables. Then, of course, you will see that the action of E is what should I say? Yeah, it's finite. It E axis, yeah, but it has like infinite Jordan block. Yes, A here is of course. And that, the existence of this logarithmic extension explains why I do have here not theta I equals theta I squared equals 0, but rather theta I squared equals theta j squared, which is action along this logarithmic extension. Now, this is, of course, not the end of this complete end of the stories, because what I really do interested are these dA modules here. And so what I'm going to do, however, is a very simple thing. So I do have a very natural function, gamma A, from weight D modules to weight dA modules. Which is the simplest thing you can think about. You just take gamma A of M is the intersection of kernels of E minus A. And so I'm studying this functor, and this functor is not always the equivalence of categories. In many cases it is, but the point is that gamma A of has left adjoint, and this functor applying to any simple is either 0 or simple again. And so I just, depending on what kind of A I do have, I usually have just an equivalence of categories, but sometimes not. So in the general, there exists an idempotent E in CK such that the corresponding block be nu is equivalent to the category of nilpotent E CKE modules. Okay? So what I'm doing, I'm projecting on the idempotence from both sides. So what does it mean from point of view of the quiver? Let me just opposite vertices of the quiver, of the cube. So if I have, so for example, k equals n equals 3, so I do have the quiver like this. Etc. Okay. But then what I'm going to do, I'm going to remove the two opposite vertices of the quiver So as a result, I'm going to get something like hexagon. And so the relations which I have, so for example, if this is alpha, beta, and gamma, and I do the parallel things here, call this beta, gamma, and alpha, then of course I do have alpha squared, for example, equals beta squared, and those are quadratic. But the problem is that I also have to put one relation, which is alpha beta gamma equals gamma beta alpha. And this is a cubic relation, so somehow the algebra which I get is not quadratic, and it seems like I lose the causality here. Also, this is the first example of the block which is not tame. because this quiver is a Weyl quiver. So the situation with regular integral case is rather most interesting situation, but I think I think I should stop now. So thank you.
Any questions? Okay. So does this all connect to this work of Musson and Vanderburg about, I mean, this, you know, this quantum Hamiltonian reduction of polynomials you wrote down here, this dA?
You know, I don't know.
Okay.
I don't.
That is a non-commutative Hamiltonian reduction.
Yeah, maybe. So, you know, I just don't know, honestly. I just forget to tell you that there is a paper of Mazarchuk and Stroppel where they work with generalized weight modules for cuspidal case. All this game can be played for generalized weight modules as well, but it's just more complicated. Now, bound Hamiltonian reductions, I should ask you after. I just don't know.
What about the next class, slide generalization of the cuspidal? So in cuspidal, everything is isomorphic.
Yeah.
Naturally, we consider isomorphism of zero.
I did discover this actually. This.
Your definition, if it's either isomorphism or zero, right?
No, for cuspidal it's anisomorphism, but I think that in our category this property is true. For each particular weight space, it's either isomorphism or zero. Yeah.